Om Swastiastu. Hello everyone, my name is Sanquerio Putra Freitas with NIM 22055311103 and I'm from Logam Paduan Industri class, Mechanical Engineering, Fakultas of Engineering Udayana University, and in this chapter 3 I will presenting to you about physical properties of materials. Okay, next is introduction. Physical properties directly affect how engineers choose material for different application. For example, we consider density, melting point, thermal, electrical, magnetic, and optical properties. These properties also affect how long a product lasts and how well it performs in service. Industries like aerospace, automotive, and high-speed machinery depend heavily on the correct balance of these properties to ensure the safety and efficiency. Okay, next. Okay, density means mass per unit volume, usually expressed in kilograms per cubic meter. Another related term is specific gravity, which compare material's density to water. Density is especially important when looking at strength to weight and stiffness to weight ratio. That's why lightweight materials such as aluminum, ceramics, and composites are so common in aircraft and cars. At the same time, high-density materials like lead or tungsten are used where extra weight is useful, such as counterbalance and weights. You can see in the figure 3.1 and 3.2 show this relationship where titanium and aluminum stand out as ideal aerospace material with the position of first and the second in this yield strength density figure ratio of maximum yield stress to density for selected metals. And figure 3.2 is the specific strength, tensile strength density, specific stiffness for various material at room temperature. Okay, next. So this is the table of the density. The table 0.1 is explaining about physical properties of selected material at room temperature, like aluminum have density kilogram per meter cubic to 2,700, with melting point at 660, specific heat at 900 joule per kilogram Kelvin, thermal conductivity 222 W per mK, and etc. And table 3.2 is physical properties of material in descending order. So there is a ranking from density, melting point, specific heat, thermal conductivity, thermal expansion, and electrical conductivity. Okay, next. Okay, now we going to melting point. So the melting point is another important properties. Pure metal have sharp melting temperature, but alloys melt over a range. The melting point defines the temperature limit in which a material can safely be used. It also affects processes such as heat treatment, hot working, casting, machining. For example, plastic have low melting ranges and are limited to low temperature use, while refractory metals and graphite can withstand extremely high temperatures, like in the figure 3.3 shows how specific strength change with temperature, explaining why composites are so useful in high temperature environment. So in the figure 3.3 is specific strength for a variety of materials as a function of temperature. Note the useful temperature range for this material are high value composite material, MMC, metal matrix composite, and FRP, fiber reinforced plastic. Okay, next. So the specific heat. Specific heat is the amount of energy that required to raise the temperature of the 1 kilogram of material by 1 degree Celsius. It controls how much heat material absorbs during processing. In machining and forming, material with low specific heat can heat up quickly, which may reduce surface quality, cause tool wear, or even alter the material structure. Understanding this property helps engineers manage heat in manufacturing operation. Okay, next, the thermal conductivity. So the thermal conductivity measure how fast heat flow within a material. Metal usually have high thermal conductivity, while ceramics and plastic conduct heat poorly. High conductivity is useful for cooling fins, molds, and cutting tools where heat needs to be removed quickly, and on the other hand, low conductivity is desired for insulation, furnace lining, and everyday items like pot, handles, or coffee cups. These properties determine whether a material should carry a heat away or keep it trapped. Okay, so next is thermal expansion. Like, all the material expand or contract with changes in temperature, and this can cause problem in assembly. If two materials expand differently, the stress may develop, leading to cracking, warping, or loosening. Engineers must consider these electronic coatings and machinery. One common solution is to use shrink fits, where parts are heated or cooled to fit together tightly. Another is to use special low expansion alloy, such as infar and cofar, which are designed to remain dimensionally stable with temperature change. Okay, next is electrical, magnetic, and optical properties. So, electrical, magnetic, and optical properties open the door to many applications. Metals like copper and aluminum are good conductor, while ceramics and plastic are insulator. Superconductor at very low temperatures can carry current with almost zero resistance, which makes useful for MRI machine and maglev train. Ferromagnetic material like iron and nickel are critical in motors and transformers. Piezoelectric materials such as quartz can produce electricity when stressed, and they are used in sensors, printers, and microphones. Magnetostriction, which is expansion of material under magnetic field, is the principle behind the ultrasonic machining. And finally, smart fluids and material can change their property instantly under magnetic or electric fields, making them useful in vibration, dampers, clutch, and even prosthetic device. Okay, next is corrosion resistant. Corrosion resistant is the gradual deterioration of material, especially metals. It's not only weaken structure but also cause industries billion every year. Corrosion can happen in different ways, uniformly across the surface, locally pits in the crevice or along the grain of boundary. Galvanic corrosion occurs when two dissimilar metals are in contact with moisture, and wireless corrosion cracking happens in material with residual stresses. To prevent corrosion, engineers are use coatings, protective films, or rely on passivation. For example, aluminum, titanium, and stainless steel form tin oxide films that protect them naturally from the further attack. Okay, next is the example of coins. A simple example of applying physical properties is a coin design. When government choose material for coins, they consider appearance, color, and even the sound of the coin. Durability is important to resist corrosion and wear. Manufacturability, resistance, and counterfeiting are also key. The material must also work in vending machine and payment devices, which test for size, conductivity, and density. Finally, the cost and the supply material must be reasonable. This example shows how even common objects like coin require careful selection. Next. And okay, the summary. To summarize, physical properties are essential in material selection, manufacturing, and product performance. Density influence whether we choose light or heavy materials. Thermal properties control fatigue and tool-life. Magnetic and magnetic properties. An electronic sensor, advanced process, corrosion and resistance, ensures long service life and reduced maintenance. Caused by understanding and applying these physical properties, engineers can design products that are safer, stronger, lighter, and more durable. Okay, this is the source that I use in this presentation. This is Manufacturing, Engineering, and Technology by Serop Kalpakjian and Stephen R. Smith. Okay, thank you. I'm Sanquerio Freitas with student ID 2205533110 and thank you.